Hello everybody. What this talk is about is interpreting microstructures. Now you can look up in books or online if it's a well-known structure, a well-known alloy, but if it's not, it's sometimes helpful to be able to interpret things and work out what's going on, and then you would look at, you maybe analyze it to find out what the phases are. So let's go ahead. First of all, we have to know what a phase is. And a phase here, you've got three phases, and they've got distinct contrasts, and they've got distinct boundaries. And they usually have a definite structure, and they exist over a distinctive temperature and composition range. So we talk about interfaces between the phases, and we talk about grain boundaries when you've got the same phase. These have just got different contrasts because they have different orientations. So here's an example of three of the most common structures that metals have: FCC, BCC, and CPH, also known as HCP. And we normally find that by X-ray diffraction. Now, it's always a good idea to look at your samples in low magnification first. Don't just stick it in the microscope and whack it up to the highest magnification, because you won't pick up the whole picture. So this, if you look at this example, you can see that there's chunks of a high melting point component. So it didn't melt. So the sample will not have the overall composition that you think it would have had if they had melted. And these you could actually see with the naked eye. With this example, if you'd gone in, you would have got, at high magnification, you would have got a bit confused about what's going on, especially if you'd gone in there. But looking at it at low magnification, what you can see is you've got an unmelted chunk of something here, although there has been some reactions going on, and then you've got layers, and then finally you've got all these chunky needles. So we know that both of these are very inhomogeneous, and once we know that, we can appreciate more that's going on. Sometimes in backscattered electrons, which is great because that gives you the average atomic number of the phases, so the lighter something is, the higher average atomic number it is, and the darker something is, the lower atomic number it is. So these needles were very rhenium rich, and then the black is virtually pure aluminium. And this is backscattered electrons, and sometimes if you look at this, you can see what's going on in the dark, but you can't distinguish these. And in here, you can distinguish these, but you can't see what's going on in the light. So you had to do it, you had to set things and change the contrasts around to work out what's going on. And then the primary phase, primary for first, is the first to form, and it grows into the liquid with much freedom because there's no other solids there. So it can form the phases that it wants. Everything else has to grow into spaces, so their shapes are defined. So sometimes you get faceted crystals. These are often compounds and bismuth. And mostly from metals, you get dendrites where they grow and they grow into arms. There's a bad micrograph of a dendrite, but a 3D one. And then this shows how the dendrite forms. It starts as a little nucleus, which is bigger than the critical radius. If it was smaller, it would just, it would have too much energy in its surface and it would just redissolve again. Then it grows and then it forms these funny shapes, and eventually it's growing into dendrites because the atoms come from the liquid to the solid in these directions. So you've got those directions coming out. And if you look at this, these are the cubic directions. And why we're interested in dendrites is that most metals and alloys start from being as cast. Even powders come from the as cast state. So it's worthwhile knowing what's going on in the as cast situation. Okay, so here we have a single phase, and what we've got are dendrites. That looks very much like a dendrite, and I think everybody would identify that as a dendrite. Here you've sectioned it so that you don't see that central spine, but you can tell it's a dendrite because it's periodic. Those arms are periodic. There's some more periodic arms there. And what's going on in this example is, although it's single phase, it looks different. And what's happening with that, it's because you've got a wide gap between the liquidus and the solidus, and quite a long composition range. And the liquid runs down the liquidus, and the solid runs down the solidus. Now, what happens with coring, because you form cores, there's the little cores, is that the first to solidify is richer in the one component, and as you carry on solidifying, it becomes less rich in that component, forming the cores until eventually it's actually more rich in the other component than it should be if it was at equilibrium. This looks horrible, and it doesn't give good properties. So normally we would anneal that to get rid of that. Here's some more examples of the coring, same picture, and just showing how extreme it can be. And here you can actually see the cores. Okay, very nasty properties, so we tend to anneal those to get rid of that. And now we've got a more interesting example where we've got two phases. This is one phase, okay, the light phase, and then the medium and the dark is also one phase, a chord phase. So you've got a hard boundary between the dendrite, and then you've got this phase, and then you've got a softer boundary in between the chord layers. And here's another example of coring, and this was aluminium, ruthenium and nickel, and this just shows a part of it. And originally people thought that these were two phases, but this proves that it's actually coring because we've got a number of samples here, and you can see they go across that whole region. And what we did is we analysed going along there between the two. Okay, so for one sample we do something like that. We also had overlap. This is the overlapping compositions. We also had X-ray diffraction peaks of both of them, and they were very well. They had two separate X-ray diffraction peaks, but they were both very broad. Okay. And then next, eutectic, and eutectic means intimate mixture, I was always told, but somebody told me it meant something else. So eutectic is two things. And this is quite fun. It shows the eutectic diagram, and it also shows a little microstructure within the different phase fields within that. And you can either get the eutectic can only be formed on this line. So the composition must lie on that line. If it doesn't, you will end up in that two-phase region, as in here, but not from a eutectic reaction. Here, you would get some dendrites of beta formed first, and here you would go straight to the eutectic. So I've drawn out the little things there, which is a sort of poor man's version of this. And here we've got another eutectic, aluminium silicon, and that's what it looks like. Okay, so you've got silicon needles in a nearly pure aluminium matrix. And what happens with eutectics, when you've got the dendrites, they tend to grow on the dendrites and grow away from it, because the dendrites would form first, the primary alpha dendrite. Now we've got the eutectic going, and it's going in that direction. There's another one going in this direction, and where they join, you quite often get a mismatch. So this just shows some examples of eutectics to show that they can have different morphologies, and this is two more examples, and both of these have got dendrites. Here's the periodic structure of the dendrites, the arms. That you can more easily see is a dendrite, and you can see the colonies, coming off of each. That little patch there of lighter, that's because it cooled fast and it had to get rid of the other phase before it could form the dendrite properly. It's not a peritectic, because these interfaces are too smooth. More about that later. And here we have another eutectic doing more or less the same thing. So it looks like you've got a dendrite, and it looks like you might have a peritectic reaction, but it's not, because these boundaries are too smooth for that. And then it looks like, well, you've got a secondary dendrite, and then eventually you get the eutectic. So this happened first, then the secondary dendrite, and then the eutectic. And this is looking at the same thing, and it's just purely by chance how we sectioned it and prepared it. You can actually see the eutectic growing off the tip of that dendrite here and here. And if you could imagine standing over here and looking back at it, you'd see that you've got these lovely you can see these lovely cones being formed. Complete fluke we got that, but very nice. Here's some eutectic colonies that are growing almost in dendrite form. There's some more eutectic colonies here, and just at higher magnification, when eutectic colonies sort of meet head on, you often get a mismatch, and sometimes people think that's a different lot of phases. It's not. Okay. Here's another example of, here we've got the dendrites and then the eutectic. And here's a nice example where you've got the dendrites, so single phase, then a two-phase eutectic, a binary eutectic, but it's within a ternary system. And now you've got what we call a ternary eutectic, which is at lower temperature than this. And here it would be the last thing to form. And you can see you've got three phases in there: dark, medium, and very light. And then you can have a thing called you can have high temperature eutectic, like here, and then one of the phases decomposes. And this is what's going on in here. It's a eutectoid reaction. So up there at 1397 is a eutectic. Down here at 1260 degrees Celsius is a eutectoid. Okay, so here liquid is going to beta and this phase, and beta is now going to form these two phases. And because that's at high temperature, it's very difficult to quench it in the binary. If you throw another element in there, you can get it. But what we've got here is, you can see this alloy composition was in here somewhere. So you had, this is now decomposed. This was beta and it's now decomposed. So that might catch you out. Here's a more famous eutectoid system in iron carbon. High temperature eutectic, which is forming this. And then the lower temperature, there's more of a gap between the temperatures in this. The lower temperature eutectoids, and it's forming these little things in there. So you've got a big difference between what we call the spacing, sometimes given the letter S, of the two phases. And that's because this is higher temperature and it's forming in the liquid where diffusion is really good. This is lower temperature and it's forming in the solid where diffusion is less good. So that's one of my favorite structures. A peritectic, which is, I have mentioned them already, which is where you've got a phase formed first, liquid reacts with it at lower temperature to form a third phase. And here are some microstructures of them, and you can see you get layers. Okay, and there's one of these nice pictures from Bailey showing the microstructures within the phase diagram. So that's the annotated one. This is a photograph, a micrograph. There's the original phase, alpha, Then we've got a peritectic reaction to form this phase, and then eventually there's a sparse eutectic, and we call it sparse because there's not very much of one of the phases, and it can be quite difficult to identify. And that's that. Here's some more peritectic reactions. So this was the primary phase. Then it reacted to form these little cubes. You can see the phase contrast is different. And this is another sparse eutectic. You can just see little bits within. And a similar reaction here. There was the original phase, peritectic to form that. And then another sparse eutectic sitting in there. Both of these systems have got aluminium in, and aluminium does seem to go for sparse eutectics. When you get a whole bunch of peritectic reactions, you get what we call it as a cascade, like in a waterfall. So here's the original phase, then you get one peritectic reaction to form that, then the next, then the next, then the next. And here they are in the microstructure, and here's the original phase. Then you've got a peritectic reaction to form that. You've got a peritectic reaction to form this, peritectic reaction to form that, and then finally, yes, it's a sparse eutectic with aluminium, mainly aluminium, but you can see a few bits in there. So you get these layers when you've got peritectic reactions. This just shows aluminium platinum phase diagram. There's different things going on there, but that shouldn't matter for us too much. So here's 81.5 atomic percent platinum in the as-Karst condition, and we're sitting in there somewhere. And what we've got are dendrites, and then we've got a eutectic, which then went through a eutectoid. Pretty tricky. Then we annealed it, and we just end up with a coarsened eutectoid, but we still got the dendrites. This is lower magnification than that. Then over here, we're in that sort of composition range. We've got needles of this phase, which I put the arrow through, and so I can't read it, and that eutectic. Okay, very nice microstructure, that. Monotectic, you don't see that often, and if you've got a composition going through there, you've got two liquids, so you can end up with one looking like drops in the other. Very strange. And then now we've got three phases, so you've probably got three components. I know that because I made the samples, and it's aluminium, nickel, rhenium. And here's the first phase to form, the primary dendrite. There was a peritectic reaction, and you can just see there. Sometimes when you slice it, you don't slice it exactly where the peritectic reaction is, but here we did. Here we didn't, okay? So a peritectic reaction, liquid is reacting with the light phase to form the medium phase. So we've got those nice big needles which grow in their own right. Then eventually the eutectic forms in the spaces between. So you can work out all that from that history. We've seen this before for our peritectic. There's the primary phase. Then you get a secondary phase forming, the peritectic reaction. And look, it looks very consumed and chewed and messy. It's not a nice even outline. And then it grows in its own right. And then finally you get the sparse eutectic. Why? Because it's aluminium. And for some reason, aluminium loves sparse eutectics. Now this looks fun, and I've got the annotated one and then the clearer micrograph. You can see you've got a very light phase, then you've got a eutectic, but the eutectic doesn't look like the medium phase is too dark to be that phase. So what's happening is liquid is reacting with this, and it's going to form two other phases. So this would be the alpha, and these would be the beta and the gamma. Okay? So you know that's happening because that phase is not that. You know, the medium phase is not that phase. That's why you can work out it's this reaction. And here's a similar one. I must admit this stumped me because my student brought me something like that, which looked a picture, which looked like dendrites, and I was just, it didn't make sense from our other results. So then I said, no, this is rubbish. I need a lower magnification figure, micrograph. And you can see that this is dendrite. It's got that periodic spacing. So we've got dendrites of that. And then it reacted to form this lighter phase. And then that lighter phase reacted with the liquid on more cooling to form the other light phase and the black. Okay, so that's what's going on there. Very tricky microstructure if you look at it in high magnification, and that's the reason why you should always look at low magnification, because when you do, you can easily see the dendrites. And sometimes it's difficult to differentiate between the phases, but there you can there as well. So you have to look at these microstructures very carefully. So in this example, they're quite difficult to see because they take up much space. You've got dendrites here, and then you get a series of other phases formed around those. And then finally, you get a eutectic being formed, which is sitting in here. Now this is made more complicated because you've got oxides here as well, which is a pain, so you just ignore them. What happens is that yttrium is very reactive and loves forming oxides, so you normally ignore the oxide phase, and you'll notice normally the dendrite forms on that, the oxide phase, normally, because it's easier to form. It's easier to form on something than it is to form in the liquid. It's like it's easier to make money if you've got some money to start off with. So here's the same sort of thing again. We got this, and you can see it's faceted. That reacted peritectically to form this phase, and then you've got little patches of eutectic. And again, you've got the oxide here being a pain, so we've ignored that because that doesn't come into it. Another example of the same system, again, we've got oxides, which we're ignoring, and you've got the there's a medium bit inside that dendrite. That was the primary phase. Then there was a peritectic reaction to form this, and then finally you had a eutectic reaction, which does look a bit strange, I admit. And then here's another reaction which you don't see that often, and I must confess, when I first saw it, it had me stumped a bit. But what's going on here, you've got the primary dendrites, they look very dendritey, and if I had this from the low magnification microstructure, I would see very easily. Then that formed the eutectic, and then you've got this lumpy thing sitting in there. And what that is liquid is reacting with both of those phases to form another phase. So we call that a strong peritectic reaction. Then this is another example of a cascade of peritectic reactions. This is the ruthenium-rich solid solution, and then it goes into the needles, and then the bits between, and so on. So you know what the clue is the dendrites. Okay, they form first, so they had the freedom to grow, so they must have formed first. Okay, then the big needles, and then the things in between the big needles. So you follow it down. Here's that other example we looked at before. Remember, we have to have two contrasts, and here's the first phase to form, that one. Then you get a peritectic reaction to form that, peritectic reaction to form these, peritectic reaction to form that, and finally you get that eutectic, and you can actually see that eutectic this time. So that's actually very nice. Then we have solid state transformations, which aren't invariant, and these can be a pain. So if we imagine we're simplifying this because both of these are ternary. If we imagine we've got a binary eutectic, which could be, in fact it was, you can assume it was binary, but it was within a ternary, but never mind about that. You will get the eutectic reaction when you go through there. But if you've got a composition here, you will form dendrites first. So you'll form the dendrites first, these shapes, and that. Sorry, my arrow should come over. No, it's my arrow should have come over more. That arrow should be there. Sorry. So we've got the dendrites formed first. Then we've got the eutectic. And then as we cool down, what's going to happen is, because this boundary comes in, you don't actually have to cross it. It will work even if it's over there. You've now gone into a two-phase region with this, and you'll get the two phases coming out. Can be quite tricky to work out what's going on, because it looks like you've got two eutectics, and you can't have two eutectics. So one of them must be a eutectoid. This just shows something similar, and what's happening here is you're going from one phase to two phase. And now we haven't got a eutectic at higher temperatures. So now we've got precipitation of that second phase. Okay, and if it's highly saturated, i.e. you're doing it quickly, so there's not enough time for diffusion, you tend to get these needles. Okay, also depends on the interfacial energy. So here you've got straight interface in that grain and curved interfaces in that grain. It's quite complicated. But here again, we call this Wiedmannstarten, where you've got something on the grain boundary and then it grows in. So there's the grain boundary. Here it is at different stages. Why do things grow in from the grain boundary? Well, there's three reasons. One is that the composition is likely to be easier for that phase to grow because it was the last to form. The second is that there's lots of nice space at the grain boundary to form the phase. And the third is the grain boundary, because there's lots of nice space, because there's two different crystal structures coming together, because there's lots of nice space, the grain boundary can act as a diffusion highway, because diffusion is easier there. So this just goes through in time, and you can see more of it coming in. Thank you very much.